Now let's study, this reverse saturation current. Our first observation is why to answer why this is basically a current. It's just a constant, but why we can call it a current. Let's look at the original equation. Of course, this equation has some derivation, but it's beyond of our interest here. We wanted to deal with analog circuits. We don't want to go deep into physics. Okay, we just use physics to understand our operation afterwards in circuits. But our main goal, our main objective is to understand circuits. Our course is called analog circuits. So we will not deal with, we will not, give so much interest on the derivation of that equation. Okay. Again, this is the equation, and we need to answer now why IS is called reverse saturation current. Why it's a current? Okay, let's look at the equation, and you will figure out. Basically, this is amperes. This has a unit of ampere. Let's check the right hand side. It should also be amperes. Okay. Let's check the bracket first. So this is a bracket. This is constant. No units, basically. How about exponential V over Vt? Whenever you see exponential, which is the natural number E, which is 2.71 something. Okay. The exponent must be dimensionless. So basically everything is dimensionless. So this exponent is dimensionless, has no unit, and that's very obvious. So V is in volt, and Vt is also volt. Remember, Vt is thermal voltage, as we studied last week. Kt over Q, electron volt. So basically, this is also a voltage. So voltage divided by voltage is just 1. So the exponent is unitless or dimensionless, has no unit, whatever you call it. So exponential V over Vt is dimensionless. So where is amperes now? So the ampere must come from Is. So that's why this has a units of ampere. And that's why it's a current. And it has a physical meaning, and we will understand why it's a current basically in a moment. Good. So Is is a current. What else about Is? If we look at this equation, okay, this equation, it should explain the relation between ID and VD. The current that flows through a diode, a beam junction, and the voltage drop across that junction. Okay, but remember, this is a beam junction. You have a material, silicon, for example. It might be germanium. Okay, you have some temperature. It might be room temperature or something else. Okay, so you might have different material for the beam junction. You might have different temperature for the beam junction. You might have different doping for the beam junction. Okay, so you should expect that with different material, different doping, different temperature, different geometry as well, the cross-section area, for example. Okay, the current should change. So where all such parameters, geometry, area, geometry of course includes the area, material, doping, where all such parameters, they are all in Is, the reverse saturation current. And here is the equation that determines Is. So Is is equal to the area A, Q, electronic charge. Basically, a current is just electrons or a charge that moves, either positive or negative, in I square. you know, the density, the intrinsic density, carrier density. And the Ni carries in it is the temperature T, because Ni is equal to 5.2 10 to the power of 15, T to the power of 3 over 2 exponential minus 2 minus Eg, the material, the energy gap, which is difference from material to material, divided by 2 kT, temperature again. Dn and dB here, which are the diffusion length, I'm sorry, diffusion parameter, or diffusion constant, or diffusivity, as we studied. And these numbers, you know, are different from a material to a material. So, for example, for silicon, dN is 34 centimeter square per second, and dB is 12 centimeter square per second. Na and Nd, the doping. And another parameters called LB and Ln, which we see for the first time. This is called diffusion length. It's basically like, you know, it's another constant like dB and dN, also depend on the material, silicon, germanium, whatever. Each one of those will have its own Ln and Lb, and it's basically the average length in micrometer, in meters, you know, that the carrier will flow before its recombination. So, for example, when holes move under forward bias, when holes moves from B to N, some of them will make it along the way until it reaches the negative terminal of the battery, and some of them will recombine inside the N-type region with other electrons. Also, electrons that moves from N to B, some of them will make it all the way to the negative, the positive terminal that is connected to the B side, and some of them will be recombined with holes there. There are holes, so they might recombine. Why not? So the average, some of them will make the recombination after 1 micrometer, another with 2 micrometer, another with after 3 micrometer, whatever. So if we add these numbers together and divide by the number of electrons or holes, we will get an average number. This average number is Ln or Lb, based on the carrier that you are talking about. It's not our story, but our story is that Is, the saturation, this reverse saturation current is a current, and it carries in it, you know, different parameters of the material, like geometry, area, the doping in A and D, the temperature in I, and also the material, because in I also, you know, different from material to material and different from a temperature to another temperature. The diffusion length, the diffusion parameter, dN or dB. Okay. So Is defines also the material and geometry of the P-N junction. And, you know, to be compatible, some text would call it I note. Just to be, for the sake of knowledge, if you read some book, you might find it Is or might find it I note. What else? Basically here, you know, on the side of that, since Is is directly proportional to the area, okay, if we double the area, then Is will be doubled. And a good model here is that if you have two P-N junctions, two diodes that are connected in parallel, you can model them as one diode, one P-N junction with double if they are matched. I mean, if they are the same, have the same area, and everything is matched, same area, same doping, same temperature, of course, because the same circuit. Okay, everything is the same. Then you can model them as you know, a bigger diode, just one diode with double the cross section area. So basically, this is equivalent to this. This is the real circuit, and this is just a model for it to make it easy for you to solve the question. Now the big question, why it's called the reverse saturation current? So we know it's a current, you know, we look at the dimensions of the left hand, right hand side of the equation of ID, and we know it must have a dimension of amperes. So it's a current. But why it's a reverse saturation current? Why it's a reverse saturation? Why it's not forward saturation, for example? Why it's a saturation? Okay. And the answer is easy. Basically, we know that ID equal to IS e to the power VD over, VD over VT minus 1. Good. We're gonna put a reverse bias, reverse voltage. So if we apply a reverse voltage, VD will be negative. It's a rule. If you put forward voltage, VD is positive. If we put a reverse voltage, VR, like last lecture with the varactor, for example, VD will be negative. Okay. So VT, which is KT over Q, it's called the thermal voltage. At 300 Kelvin, VT is approximately 26 millivolt. Good. Let's put VD, let's put a reverse voltage, you know, such that VD is equal to minus 10. So assume VD is equal to minus 10 volt. Remember, this is 10 volt, minus 10 volt, and the other guy is 0.026 volt, which is 26 millivolt. Okay, I'll give you 1 minute. You can just pause the video and try to find just that portion. Don't worry about IS. Just calculate on your calculator E to the power of minus 10 over 2.26 to 0.026 minus 1. I hope you solved it. So you will find some very weird result. This is equal to minus 1. I should say approximately equal to minus 1, but if you did it, you will find it minus 1. It's just it's a fact that it's minus 1. It's approximation, of course. But basically, your calculator cannot, you know, put 0.0000 and put, you know, whatever zeros, maybe 1,000 or something, then put 1 at the end or something. Okay, that's why it's minus 1. So because this is very, very small, e to the minus 10 over 26 milli or 0.026 is very small. It's 0. And it's just a math fact. Okay, if we increase e to the minus 1 is greater than e to the minus 2, greater than e to the minus 3, okay, until, for example, until you reach infinity. And actually, e to the minus infinity is just 0. Like, for example, half, okay? Half is greater than half to the power of 2, which is 1 over 4. And basically, half is greater than quarter, which is greater than half to the power of 3, okay, which is 108, 1 over 8, and so on. So this is basically equivalent to saying that 2 to the power of minus 1 is greater than 2 to the power of minus 2, 2 to the power of minus 3, until to the power of minus infinity, which is just 0. Half, quarter, 1 over 8, 1 over 16, 1 over 32, 1 over 64, until, you reach 1 over infinity, which is just 0. That's exactly what we have here. Usually, that's why this happens, because usually VD as a magnitude, I mean minus 10 magnitude, which is 10, is much, much larger than VT, which is 26 millivolt. So most of the time, when the applied voltage is reversed, you will see that the current cannot increase than, as a magnitude, of course, than minus IS, because if you go back here and substitute, this will be IS multiplied by minus 1, it's minus IS. So in reverse condition, under reverse condition, the current that will flow most of the time when VD is much greater than VT, which is most of the time, okay, will be minus IS. That's why when we draw the complete relation, ID equal to IS exponential VD over VT minus 1, we're gonna see that relation here. Here is the forward bias part from here to infinity, and here is the reverse bias part. And just forget about the forward part. Just look at the reverse part now. In the reverse part, you will notice that all over, whenever we are negative, the current is constant, equal to minus IS. Except a very, very, very small portion at the beginning near 0, in which VD is, as a magnitude, of course, is less than, or comparable, we can say comparable to VT, like for example 10 millivolt, 20 millivolt, 30 millivolt, 50 millivolt even. Okay, so at these values, which are comparable, so might be a little less, a little larger, but it's comparable to VT. In that portion only, we're gonna see some increase in negative, we can say. Very small region. So this region here, let's make it with another color. This region here, VD as a magnitude, of course VT is negative because this is reverse, is comparable to VT, which is 26 millivolt. All the time we deal with or we assume room temperature. So VT in room temperature is constant, equal to 26 millivolt, around 26 millivolt. Okay, good. So we know that IS is a current, and we know it's a current that will flow in reverse. And we know why it's saturation, because most of the time in reverse, whenever VD is much larger than, much greater than VT, this exponent will be just equal to 0. So ID is all the time is equal to IS multiplied by 0 minus 1. So it's multiplied by minus 1. So ID is equal to minus IS. So it's saturation, saturated. It cannot increase. It cannot go beyond IS or minus IS. Now, as a physics, what is this current exactly? We know it's flowing in reverse, but why in reverse? Let's see. Okay, let's have a reverse connection like this, and let's try to understand what are these carriers. That because a current needs a carriers. Current needs a carrier. So we now know that there is current, although we said last time there is no current in reverse. but now we are contradicting ourselves because there is a current, but it's very small, as we will prove or see now. Okay, and we will prove it twice by the understanding the physics and by example. So there is a current, so we need to know its carriers. So we said that under reverse bias conditions, holes cannot move in that direction. They cannot move because they will be expelled by this, there is here a built-in voltage and a built-in electric field. Okay, and holes or positive carriers want to move in the direction of the electric field, so they will go in that way. Actually, they will go to the negative terminal of the battery and absorb it there, and the electrons will move in that way. So this is holes, and these are the electrons, will move in that way, away from the junction. Okay, but we know that there is minority carriers inside the B side and other minority carriers inside the N side. So let's do that with another color. So we know that there are electrons here in NB, and there are holes in the N side, Bn. And remember, Bn has positive charge, are positive carriers, and NB are negative carriers. Let's see how they will interact with the built-in potential or built-in electric field. Good. So Bn want to move in the same direction of the electric field, so they will move in that direction, crossing the junction, and they will make a current. Let's call it I reverse, because this is reverse. I reverse B. Let's call it I reverse B. And the electrons will move in the opposite direction of the electric field, so they will move in that way. So they will make a current, but this current is opposite direction as well. So the current is in opposite direction, so this is I R N. So I R N and I R B are both in the same direction. And basically this is IS. So IS is basically IRN plus IRB. This is minority carrier current. Minority carrier current. So why it's small? Because it's a minority carrier. That's why IS is very small, approximately zero. You can consider it zero, and in we can say in 85% of the course we will consider IS is zero. And we know now why it's small, because it's the current of minority carriers. Remember, minority carriers are very small compared to the majority carriers. We are comparing, like, for example, 10 to the power of 4, like we see in the examples before. In one of the example, hole concentration was 10 to the power of 4, and at the same time, the electric concentration was 10 to the power of 16. So let's solve an example. This example is actually in the book, and it also refers to another example, as you read here, but I will summarize the situation for you. So it's basically asked to determine IS, the reverse saturation current, when T is 300 degree Kelvin. Okay, so basically when you hear that T is 300 degree Kelvin, so we can say this is in I is equal to 10 to the power of 10 carrier per centimeter cube. Okay, the area, the cross section area is 100, so area is 100 micrometer square. Ln and Lb, these are the diffusion lengths, as we said, for the holes or for electrons first is 20 micrometer. Lb is 30 micrometer. Okay, good. So we know Is is equal to Q, which is 1.6 10 to the power of minus 19. The area is known, 100 micrometer square. Then let's check the equation here. Ni square 10 to the power of 20, because it's a square, it's 10 to the power of 10 square to 10 to the power of 20. And now you have a problem. This should be converted. So it should be converted to centimeter. Okay, centimeter square, of course. Then in a bracket, dn over ln Na. Na can be get from this example. So Na and Nd is mentioned there. This is Na and dn ln. Dn for, since this is a silicon, so dn is 34. And remember, this is centimeter square second. And this was in centimeter cube per centimeter cube. So you must convert the ln, which is 20 micrometer. You must convert it to centimeter. Okay. Plus dB, which is 12 centimeter square second, over nd. Remember, this was in centimeter minus cube or minus 3 or per centimeter cubed. lb is 30 micrometers. This also should be converted to centimeter. Okay. Just, compensation. It's not, so it's very very substitution. Good. If we calculate all of that, Is will be 1.77 10 to the power minus 17 ampere. Look how small it is. We know it's a minority carrier current, and now, using just direct substitution with practical numbers, you see now how Is is very small. It's extremely small, extremely small. In next recording or next video, we're gonna check other important properties for ID and VD, how they change, how they react to the change in one another. Okay, then we will see or examine, our first circuit, in which we put the diode, okay, and try to analyze the circuit, find its current, find its voltages, okay, which is, the real beginning of that course, because till this moment it's just physics. Okay, so next lecture will be, or next videos will be the real start of the course. Okay, guys, thank you very much for listening, for watching this video, and see you in the next videos. Bye-bye.